All right, so welcome to section 2.4. The definitions we're going to be taking a look at in this section are continuity and one-sided limits. So the title is Continuity and One-Sided Limits. Our objectives are to take a look at the idea of continuity at a point and continuity on an open interval. Take a look at some one-sided limits and then use that to talk about continuity on a closed interval. Use properties of continuity, and what we're going to do is we're going to say, okay, where is this function continuous based on properties of it? And lastly, understand and use the intermediate value theorem. All right, so we're going to start by taking a look at the idea of continuity at a point and then extend that to an open interval. All right, so what we're going to talk about is the idea of continuity, or when is a function continuous. And it pretty much in math means the same thing as it would anywhere else. If a function is continuous, it means there are no interruptions or breaks in the graph. All right? So to say that a function f is continuous at a point x equals c means that there is no interruption of the graph there. There's no break in the graph, there's no jump in the graph, there's no asymptote, vertical asymptote that occurs in the graph there. Right? So basically, our quick and dirty definition says that if you can draw the graph of a function without lifting up your pencil, you're continuous. If you have to lift your pencil up to draw a hole or to break the graph, then you are discontinuous. Okay? These graphs over here I have, these graphs right here, define three different ways that a function could have a discontinuity at a value c. Okay? First one over here on the left. Okay, this first one over here on the left is just straight up, there's a hole in the graph. So it is discontinuous because the function is not defined at c. Okay. The second one has a discontinuity. This is referred to as a jump discontinuity or a break discontinuity. And basically what's wrong here is the left-hand side of this piece of the graph doesn't line up with the right-hand side. Right? There's not a hole in the graph because the function is defined at c. Just the graph is broken. And because the graph is broken, it has a discontinuity. Right? Now the one over here on the right, it is also discontinuous at c. Even though the graph is defined at c, there's still that hole in the graph. Okay? So let's take a look at the definition mathematically of the continuity and see why each of these pieces fails our mathematical definition. Not just the quick and dirty, there's a hole, there's a broken, or there's a hole. Right? For a function to be continuous at a value c, so for a function to be continuous at a value c, there are three conditions that must be met. One, the function must be defined, f of c must be defined. Right? Two, the limit must also exist there. And three, the limit of the function at c must also equal f of c. Right? So these are the three definitions of requirements for the definition of continuity. Right? But we often use these definitions to define discontinuities. So if I go back up here to my graph, we said that this one was discontinuous at c. And why is it discontinuous at c? Which one of these definitions down here, or these parts of the definition down here, does it fail? Right? We always start at the top and work our way down. Is f of c defined? Nope, there's a hole there. It's not defined, therefore not continuous because it is not defined. Right? Graph number 2. Right? Again, to figure out where it is discontinuous or why it is discontinuous, we start with the definition. Is it defined? Yep, it is. That solid dot right there says f of c is defined. So number 1 is good, or number 1 is not violated. All right, so the function is defined, so number 1 is good. But the limit doesn't exist because the graph is broken, so number 2 fails. So we would say that that graph is discontinuous at c because the limit does not exist. Okay? Then let's take a look at number 3, this graph on the right over here. Number 1 is good. The function is defined. Number 2 is good. The limit exists. Coming in from the left, coming in from the right. We're at the same y value. Number 3 fails because the limit is some value up here and the function is defined for some value down there. So this is our limit, and that's f of c. They're different, and because they're different, the limit is not equal to that f of c value, and the function is discontinuous. Now, the idea of continuity at a point can be extended to talk about continuity on an interval. And we say that a function is continuous on an interval if it's continuous for every single point in that interval. And if a function is continuous on every value, from negative infinity to positive infinity, we say that it is everywhere continuous, or continuous everywhere. Now, continuity is a great thing to know about, but the reality is we don't really ever talk about continuity directly. We talk about discontinuities. And if we want to talk about continuity, we look for discontinuities, and we say that if a function has no discontinuities, then it's continuous everywhere. Okay? Continuities fall into basically two categories. Okay? So when we're looking for discontinuities, they fall into two basic categories. That is the removable discontinuities and the non-removable. Removable discontinuities are basically a hole in the graph. This is a removable discontinuity, and this is a removable discontinuity. We could fix the first one by just simply filling in the hole and defining f of c. We could fix this one by just moving that point up. Okay? This is a non-removable discontinuity. We can't fix that one. We'd have to bend the graph to get those two pieces to come together. And if we bent the graph to get those two pieces to come together, then it is no longer the same graph, and we've fundamentally changed it in a way that isn't good. Okay? So, continuities and discontinuities. We really use these definitions up here not to check for continuity, but to check for discontinuities. If any of these fail, we say that the function is discontinuous where they fail. Okay? Questions are going to look like this. They're going to say things like, discuss the continuity of. And when they say discuss the continuity of, what we need to do then is look for discontinuities, identify where it is discontinuous, get rid of those bad values. What's left is where it's continuous, and that is going to be the discussion of continuity. For example, here I have the function f of x is equal to 1 over x. Right? I know what that graph looks like. I've graphed it so many times. Hopefully you have too. It looks like this. If you don't know what it looks like, get your favorite graphing tool out and take a look at the picture. It looks like that. Okay? Has a horizontal asymptote at y equals 0, has a vertical asymptote at x equals 0. Are there any places where it is discontinuous? So hopefully you're seeing that this is discontinuous at x equals 0. Well, if it's discontinuous at x equals 0, where is it continuous? Continuous, yeah. Well, it's going to be continuous from negative infinity to 0, union with 0 to infinity. Okay? By the way, why is it discontinuous there? And don't say vertical asymptote, because that's not acceptable. Which one of these three does it fail to make it discontinuous? Okay, well, right there, first one. F of x equals 1 over x is not defined for x equals 0. And because it's not defined at x equals 0, it is a discontinuous function at 0. Right? All right. How about g of x here? What is its continuity? Now, hopefully you're seeing the same thing I'm seeing. There's an issue at -1. From all that limit work that we did, I'm recognizing that if I try to plug in a -1, I'm going to get a 0 upstairs as well as a 0 downstairs. And if I think about all that work I did back there in the last section, what is this? Okay. That is a hole in the graph, which means that if I were to make a quick sketch of this thing, the graph of this is going to look like this. It's going to look like a line with a slope of 1 and a y-intercept of -1, and it has a hole in it when x is -1. So where is it continuous? Well, it's continuous out here, and it's continuous over there. So it is continuous from -infinity to -1, union with -1 to infinity. And what kind of discontinuity is that? Well, we have a removable discontinuity at -1. What kind of discontinuity is this? Well, it is a non-removable discontinuity at x equals 0. To fix this, we'd have to bend the graph to get those two ends to come together. It's not just a hole to fill in. That's not going to work. Okay? How about this guy? Well, things are getting trickier because we have some sort of a weird function here. We have a piecewise defined function. And so if I try to make a quick sketch of this thing, right, less than 0, it looks like x plus 1. So over here to the left, it's a line with a slope of 1 and a y-intercept of 1. To the right of 0, it looks like e to the x. Let's see, e to the x, e to the x, e to the x, is that this guy? Exponential function, crossing the y-axis of e to the 0, which is 1. So it's going to come off of here like this. So even though this is a piecewise defined function, look what happens here. The line and the exponential come together. So where is this thing going to be continuous? Well, again, I don't look for continuity. I say, where is it discontinuous? And if, here comes the double negative, if it's discontinuous nowhere, then it is continuous everywhere. And so we would say that this thing is continuous on the interval -infinity to infinity. How about sine x? Where is it continuous? Well, if I make a graph of sine x, there's one standard period, and then it repeats, and then it repeats. So are there any holes or breaks or jumps? Now, I did draw this dash, but you know that this is continuous, right? I just drew a dash because we normally just talk about one period. No holes, no breaks, no vertical asymptotes. There is nothing bad. So there are no discontinuities. So this thing is continuous everywhere. Negative infinity to positive infinity. I'm liking this continuity stuff. This is pretty straightforward. All right, so let's make it harder. One-sided limits, continuity on a closed interval. Right? To understand continuity on a closed interval, we first have to take a look at one-sided limits. But this is nothing new. We're just actually giving a name to something that we've been using for a good while now. Now, every time we've taken a look at the limit of a function, we've said coming in from the left, where is it going? Coming in from the right, where is it going? So every time we took a look at a visual, a graph, we said, where is it going? Where is it going from the left and from the right? All we're doing is giving this a name. Right? So what we're saying is, if you're taking the limit at c, and you're approaching from the left-hand side towards that value, that is a left-hand limit. The notation that we use is we use this little negative symbol in the exponent position. That does not mean that c has to be a negative number. That just means we approach c from the left-hand side. So a left-hand limit, a one-sided limit. All we're doing is giving a name to something we've already used. We've said, what does the function approach when you come in from that left side? And so we're talking about a left-hand limit. Okay? If that's a left-hand limit, then what's this? Okay? Well, we're coming in from the right-hand side, so we have a right-hand limit. If we use a little negative for left-hand limits, we're going to use a little positive for right-hand limits. Now, here's where people get screwed up on this. If you are taking a left-hand limit, you are actually moving right on the graph. And if you are taking a right-hand limit, you are moving left on the graph. So it isn't about which way you're moving, it's about where you're coming from. Are you coming towards the number from the left of the number, or are you coming towards the number from the right of the number? Left-hand limits come in from the left, right-hand limits come in from the right. Right? We can use it to talk about things like this graph here in the middle. We can talk about the left-hand limit being up here, and I'm just going to make up a number 5. And we can talk about the right-hand limit being down here, say 3. And we can say that the left-hand limit is 5, the right-hand limit is 3, and since the left doesn't match the right, the limit does not exist. Okay. Now, if you're wondering where 5 and 3 came from, I made those numbers up. I just needed numbers to talk about, so I just put them on the graph. Okay. Okay. So, one-sided limits. Let's take a look at these here. So here I have a beautiful picture, and I have a whole pile of limits over there. 9 limits that we have to calculate. Okay. We're going to start in the upper left-hand corner. We're going to find this limit first, right here. And so let's take a look at that notation. It reads, find the limit of the function f of x as x approaches -4 from the left. How do I know it's from the left? Because of that negative right there in that exponent position. So I'm approaching -4 from the left. -4 from the left. -4 from the left. -4 from the left. What am I approaching? What is the y value that I'm approaching? Well, I think I'm approaching a y value of 2. Right? I'm going to work my way down that column. Right? Do this problem next. Ask me to find the limit of f of x as x approaches -4 from the right. I know it's from the right because of that little positive in the exponent position, right? All right. So now I come over here and I say -4 from the right. What's the y value that we're approaching? 2. And then the third one, what's the plain old limit as x approaches -4? Well, from the left we were going to 2, from the right we're going to 2, so we're going to say that since the left matches the right, our limit is 2. If the left-hand limit matches the right-hand limit, that is the limit of the function. All right, let's take a look at the next column. I'm here. I'm taking a look at the limit of f of x as x approaches 1 from the left. So 1 from the left is coming in right here. And it looks like we have a y value that we're approaching of 4. Okay. One from the right. Well, we're down here now. So we're following that graph up, and it looks like we have a y value of a -2. If the left is 4 and the right is -2, what's the limit? Well, the limit only exists if the left-hand limit and the right-hand limit are the same. And so the left-hand limit is 4, the right-hand limit is -2, the limit does not exist. One-sided limits can exist even if the limit doesn't exist. But the limit can't exist unless the one-sided limits exist. All right, more, because this is exciting. How about that left-hand limit at 6? So left-hand limit at 6 looks like 5. Right-hand limit at 6, also 5. Limit at 6, 5. Doesn't matter down here. Okay. Hey, as long as we're looking at this graph, where is it discontinuous? Well, it has a discontinuity at -4. It has a discontinuity at 1. And it has another discontinuity at 6. Okay. This is removable. This one is removable. This is not removable. We can fix the one over here on the left at -4 by just filling it in. We could fix the one at 6 by just moving that point up. But I can't fix this one because my graph is broken there. Okay, the pieces don't match up. All right, so here we get the final definition of a limit. Says that you only have a limit at C of L if the left-hand limit is L and if the right-hand limit is L. Now, we've been using this definition for a while. We just didn't have the notation or the terminology to call it left-hand limits and right-hand limits. We're at 23 minutes, so I'm going to end this video here and come back and we'll finish the rest of the section in the next video. So I'll see you all back here for part 2.